I'll figure it out. Okay, so chapter 17 is like chapter 16, but easier because it's really simple and there's like one reaction that you have to keep in mind and everything else is like the same. So the very first thing is like properties of carboxylic acids. No one really cares about it, but it shows up, so we'll do it. So carboxylic acids have a higher or lower boiling point than alcohols. Any guesses why?
Because it has.
Okay.
Like they share the electrons.
They do. So they share electrons through H bonding. They're not concerned about resonance. So this is actually like interesting. Out of all the boiling points ever, this is the only slightly interesting one. So the reason carboxylic acids have a high boiling point is because of this. So let's say we have these two carboxylic acids. They're just like floating in the solution. So what can happen here is H bonding between the H and the O. So on the top, like that alcohol is going to bond with the carbonyl carbon, and on the bottom, that H is going to bond with the other carbonyl carbon. So that makes a 6-membered ring, which is the most favorable kind of ring. All the bond angles are good, and this like kind of pseudo cyclic thing makes it really stable, doesn't really want to break and boil. Yeah, so that's why. And rank the following order of acidity. Okay, so out of all those 3 kinds of oxygen things, which one is the most acidic?
Would be the carboxylic acid the most.
Yes. You don't?
Alcohol.
Yeah, why would it be phenol? No, that's it. Resonance. There's no other difference between phenol and a normal alcohol. So phenol is this. Normal alcohol is like whatever. So the only difference between these two, the OH is the same, but with phenol, when you deprotonate it, you get this, and this can do resonance within the benzenes. When you deprotonate the alcohol on the right, like the charge just sits there, it can't go anywhere. So this sucks. So carboxylic acids have like the super resonance between 2 oxygens. Phenol has that resonance within the benzene, and alcohols have like nothing. So it's 1, then 2, then 3. Okay, so looking at this little matchup of acids, what kind of functional group do you think makes the carboxylic acid more acidic? Okay, yeah, close, but what is the property of halogens? Yeah. So we're gonna say electron withdrawing groups make carboxylic acids more acidic. So any guesses why? Fair enough. So all you have to do, acidity is the measure of like how easily the proton is willing to like jump off. So we're measuring how willing the proton is like to leave its molecule. So let's say like we have this carboxylic acid, let's say the proton left and we have a conjugate base. So that conjugate base around that oxygen, because it has a lone pair, there's a lot of electron density just sitting on it. So when we stabilize a conjugate base, what we're doing, we're just like distributing that like electron density. So when we stabilize something, all we're trying to do is like kind of distribute this density among the molecule. So it's not all just like sitting on one oxygen. So like that is distributed through the resonance here and also through the induction. So this fluorine is like the most electronegative molecule ever. So that is going to withdraw a lot of electrons. So through induction, it's going to take away a lot of the stress from the oxygen, so it makes it more stable. So we're going to say electron withdrawing groups make carboxylic acids more acidic because they stabilize the conjugate through induction. So naturally, if you want to make a carboxylic acid more acidic, you would have more halogens, more fluorines because they're most electronegative. And ideally, you want the fluorines as close to the oxygen as possible. Because the closer it is to the oxygen, the more it's going to be able to like stabilize it through induction. Because inductive effects wear off the further you get. Okay, so out of the first two, which one is more acidic, the left or right? Yes, the right. So there's more fluorines and they're closer to the oxygen. And then what about the second one? The left, because fluorine is much more electronegative than chlorine. Okay, so now we have nomenclature. I started with esters just because I'm not going to start with the first one. Let me start with the very last one. So how you name esters, you kind of just take both of like the alkyl groups, so like the left alkyl group and the right alkyl group, and you kind of just like arrange them. The first thing I'm going to do, I'm going to count like the length of the left carbon chain. So the carbon chain that's coming out of the carbonyl. So that's 1, 2, 3, 4. That's going to be like a butane. So I'm going to put butane. Then I'm going to count the right side. So on the right side, whatever's coming out of the oxygen is 1, 2, 3, 4. That's also butane. So we have two like butyl chains. So the one that's connected to the carbonyl, the one that's coming out of the carbonyl, that's going to be the parent chain. So that's like in the later half. The one coming out of the oxygen, so this butyl, that's going to be like the substituent. So I'm going to arrange it like this. I'm going to say butyl, butan, and then the suffix for esters is always O8. So, yeah.
You said the second part was,
Which second part?
you said the one on the carbonyl, the parent.
So the second chain is the substituent in front of the parent chain. So like that butane coming from the O became the butyl.
The O comes from double bonded oxygen.
The O8, like every time you're naming an ester, always ends with O8. So how do you think we would name the second one?
Would it be isopropylpropane?
Yes, it would. So so we saw the isopropyl on the right. So that's the one connected to the oxygen. So that's going to become like the substituent. So we're going to do like isopropyl because that's the substituent. And then on the left, we have the 3 carbon chain coming out from the carbonyl. So that's our parent propane. So we have isopropyl as a substituent, and then propan, and then O8 because it's an ester.
They should like came up with longer.
Why? But this is fun. Okay, so what do you think we named the first one?
Hold up.
Yes?
What do you call that? Bro?
No.
I was gonna say, so is turbulate part of it?
Turbulate?
I mean, it sounds like,
Yeah, turbulate is part of it.
okay.
Yeah, okay, so when you have a benzene with a bromine on it, it's called bromobenzene. So so now what do we think our little parent chain is gonna be? Mhm.
Benzo or bromobenzene, no.
No. Okay, so that's really close, except you're off by a few letters. So tert-butyl is right, because tert-butyl is the oxygen substituent. That's tert-butyl. And okay, so this bromobenzene, the bromo could be literally anywhere on the benzene, so we have to specify the position. Yeah, we could do two. What else could we say? Meta. So I prefer saying meta. Oh shit. Meta. And what did we say the whole thing was called? Bromobenzene. Bromobenz. But saying benzenoate sounds stupid, so we cut off the ene and add OH. Yeah. Okay, so I don't
I have
think.
a question.
Yeah, go
One
ahead.
of the tests is met oxide, is that a deactivator or activator when it's a methyl to an oxygen?
That'd be an wait. No, it'd be an activator, either way. So even if like,
So when it's a methyl, CH3O,
so you
you have the oxygen.
CH3O.
What does this have to do with check? Because I just remember, yeah, like that.
Yeah, that's an activator. It's an OR. Okay,
Sorry.
it's fine. So acyl chlorides. I don't think you have to know nomenclature of acyl chlorides. But it's really stupid, so we should just do one. Okay. So for acyl chlorides, all you do, you name it as if it was a carboxylic acid, and then you drop the ic acid and add ill chloride. So if you think of the molecule as a carboxylic acid, you name it accordingly. And once you've named it, you drop the ic acid and add ill chloride. So I think the second one is a good example. How would you name that as a carboxylic acid if it wasn't a Cl and if it wasn't OH? Huh. This back to our little benzene skeletons. One second. Yes, it would be benzoic chloride. So as a carboxylic acid, if this was an OH, this would be called benzoic acid. But we drop the ic acid and we add ill chloride. So it's now benzoyl chloride. That's how you name all of these. Okay, so carboxylic acids. Do we know how to name these? Yeah, there is an ic involved. Yeah. So what would we name that first one? Yes. Well, okay, no. No, we're out of the oils now. We're back to egg. Huh?
So it would be 3, 4
You're
times.
so close.
Oh, so I forgot the metals.
Yeah, but you're also so close after that. Yeah. Okay, so we find the parent chain, which is this pentane. So we're starting with a pentan something. And it's a carboxylic acid. So we add oic acid as the suffix. Pentanoic acid. And then we have some substituents. We have a methyl on 1, 2, 3, 4, 5. We have a methyl on 2 and 3. So it's 2,3-dimethyl pentanoic acid. Okay, what would you name the second one?
Not just like carboxylic acid.
No. No,
Wait, what does carboxylic acid normally look like?
it's a functional group.
Oh. Well, it's like ketone.
No, there's no molecule or like carboxylic acid ketone
So
outside.
maybe ethanoic.
Yes, it would. It would be ethanoic acid, but what else could it be?
Um,
No, the ethane is still there. But what other like weird functional group did we discuss at some point in time? We had the acyl and then the acetyl, right? Huh? What?
I just did it again.
Okay. So we talked about this. We said this was an acyl group where you have a carbonyl connected to an R. That is acyl. This is acetyl. It's an acyl group, but instead of like any R, it's a methyl. It's always a methyl. So a carbonyl with a methyl sticking out of it is always acetyl. So what you'll see for molecules like this, instead of like saying ethanoic acid, people will say like acetic acid. So this is also known as acetic acid. And it's not acetoic acid because they're like rule breakers.
What's the difference between the top left and hardcore?
What?
The top right is only methyl.
Oh, okay. Gotcha.
Okay, so last one isn't even a carboxylic acid, so I'm not sure why that's there. So, but do you know the common name of this? Formaldehyde. That's important. Just remember that. Okay, so then we have nitriles, but no one cares about those, so we're moving on. So now we have our mechanism, which is nucleophilic acyl substitution. So this is the idea for this entire chapter. It's just one mechanism, you just apply it and copy and paste it to different molecules. So in this chapter, we're dealing with these carboxylic acid derivatives. So in a carboxylic acid, you have that OH. So this OH, you can do stuff to the carbonyl because the OH acts as the leaving group. So if you remember, like if we have reduction or a reduction, like when you attack the carbonyl, first you remove the OH and then you remove the carbonyl. That doesn't matter. The point is this thing over here attached to the carbonyl is a leaving group. So when we have our carboxyl derivatives, like all of these, the leaving group here, instead of being an OH, it changes to like various other things. So for the general mechanism, instead of OH, I'm just going to put leaving group because it could be anything. So now we're going to give this thing a nucleophile. So we're going to give it a protonated nucleophile, and the nucleophile is going to attack the carbonyl carbon because it's electrophilic. The carbonyl carbon is delta positive always, so the nucleophile can go in and attack. So the next step, you have this thing, which is called your tetrahedral intermediate. So I have my leaving group attached still. And then I have my nucleophile attached as well. Okay, so all we did, we just glued the nucleophile on there. Those electrons, the carbonyl carbon, they went up to the oxygen. So now the first and last time I'm ever going to draw protonation for this class, there's going to be an intermolecular proton transfer. So the H from the nucleophile is going to kind of glue itself onto the leaving group. So now I have this. I have a protonated leaving group, which is now plus charge because it has one extra bond. And then I have the nucleophile that's now just like attached. So the last step is the electrons that are floating up here on the oxygen are going to come back down. So they're like, okay, we can reform the carbonyl. So I'm just going to go ahead and do that. So the electrons come back down, they remake the double bond, and in the process, they kick off the leaving group. They kick off the protonated leaving group. So now in my final product, I'm left with this. So in the final product, all I did was replace the leaving group with the nucleophile and protonated the leaving group. That's all that happened. You can skip like the middle stuff. No one really cares about it. So all you have to do whenever you think of this reaction, whenever you see this reaction, you're going to cut off the original leaving group and paste on whatever nucleophile you have every time. It's not like 16 where like each reaction is different. You have to memorize it. That's like basically it, except for like one thing you have to keep in mind, which is the reactivity. Okay, so these are all of the carboxylic acid derivatives that we care about. So in order, the very first one as a functional group, it's called an acyl chloride. It's acyl chloride or like acid halide. I don't know, you can call it both. But it's called that because you have your acyl group and then you have a halogen. So yeah. So your acyl chloride is more reactive than this thing, which is called your acid anhydride. Oh, and for the leaving groups, like in the first one, instead of an OH, we have a Cl there. So Cl is now the leaving group. So Cl is a very good leaving group because it can like stabilize itself as a halide ion. It's always been a really good leaving group because of stability. So then the acid anhydride, it also has the leaving group. So instead of the OH, we have literally just like another carbonyl. We have another like acyl group. So that whole thing is the leaving group for an acid anhydride. And if you can tell, that is also very stable because there's a bunch of resonance happening. So like once this oxygen becomes negative, it does resonance with the carbonyl and it's really happy just floating on its own as an ion. Okay, so an acid anhydride is more reactive than a thioester, which is this. So with a thioester, we just got rid of, it's basically an ester, but instead of an O, we put an S there. So it becomes thio. So a thioester is more reactive than these two. So this is your ester and carboxylic acid. We rank them as like the same reactivity basically because like the leaving groups, the OR and the OH are like basically equivalent. So they're of the same reactivity. And then the least reactive of them all is your amide because the NH2 is the worst leaving group. Okay. So we did that, we labeled the leaving groups. Because there's one more thing you have to consider for reactivity. So it's not just the leaving group that you have to look at, it's also the sterics. So if you remember like from chapter 12, I think, the more induction you have, or like the more bulk around the carbonyl, the harder it is to like reach the carbonyl carbon. So think if you have a nucleophile, it's much easier to attack the one on the left because there's less like steric hindrance around it. But the one on the left has this like giant chunky terbutyl, so it's a bit harder for the nucleophile to like get in there to the carbonyl carbon. So the one on the right, whichever one has less hindrance is going to be the more reactive one.
So the nucleophile still is able to react, correct? It's just,
Oh, the one on the left?
yeah, it is able to react, it just takes a really long time.
Yeah. And you get like bad yield. Okay. So technically there are a bunch of reactions for chapter 17, but if you just consider the general mechanism plus the order of reactivity, like you don't have to memorize all of them. But the first one you do have to memorize. So the first one is acid chloride synthesis. All you do, you give a carboxylic acid some kind of like halogen protecting group. So we can give this Sokal 2, which is, I think, their favorite. You can do Sokal 2, you can do like PCl5. You could even do like sober, SOBR2, or like PBR3, like whatever. Anything, any protecting group that has a lot of halogens, all that does, it is the same thing. You cut off the oxygen and replace it with whatever halogen you had. So that way we go from a carboxylic acid to an acid chloride. Okay, so let's see, there's a bunch of reactions we can do with acid halides now. So from an acid chloride, if we go back to our reactivity thing, the acid chloride is the most reactive out of like all the carboxyl derivatives. So the general idea here is that if we give it like any nucleophile, like this is willing to turn into any of these. We'll see. So it's really easy to go from an acid chloride to any other derivative because the acid chloride is the most reactive. Okay, so we give an acid chloride H2O. Let's start with that. So if we give it H2O, what do you think is going to happen? Like, what would this reaction give you? Exactly. So our H2O is our nucleophile. It does what we just said would do in the mechanism. It's just going to attack the carbonyl carbon and then kick off the leaving group. It just replaces the leaving group. So instead of the Cl, we now have an OH. So this is a carboxylic acid. The next thing we can do, let's say we give it an alcohol. What would that turn into? Exactly. So we just cut off the H and then replace the Cl with that. We have our ester. Then what if I gave it this molecule? What if I gave it like an acetate ion? It would give you an anhydride. So the acetate is going to attack the center again, and it's just going to replace the chlorine with itself. So we just attacked that, like we just added that whole thing on as a nucleophile, and we got an acid anhydride. And then we can do, let's say we said NH3. That would give you an amide. For the amide, this applies to every time you make an amide. So like when you use the amine as like your nucleophile, it could either be NH3, or it could be like a primary amine, so like RNH2, or it could be a secondary amine like R2NH. Like any of those forms of amine is like acceptable. Okay, so there's a couple more. The other one is like reduction. So by reduction, I think Wes just says like H minus. He doesn't give you the actual reagent. The actual reagent is H4. Okay, so that's the actual reducing agent used for acid chloride. So this like word vomit is going to turn the acid chloride into an aldehyde, but you don't have to know that. So you can just like express it with H minus, which is a reducing agent. You can just write H minus, or you can write that. LiAlH4OTBU3. No, no. I just like feel gross, like giving you just H. So yeah, I wrote the full thing. Probably neither, to be honest, but it's in his PowerPoint, so I put it here. Okay, so this is going to turn it into an aldehyde. And lastly, if we give this a Grignard, like you just replace the OH with, oh, actually, no. Yeah, you replace the Cl with the R. But for Grignard, I highly doubt you're ever going to see this. For Grignard, instead of just like one attack with the R, you attack it twice because it has a leaving group. Because like the R goes in, first gets rid of the chlorine, and then the second attack gets rid of the carbonyl to get an alcohol. But honestly, like you can just ignore the Grignard completely.
So if it was a primary NH3, you were adding an NH3.
Oh no, so anytime you do like an attack, you always just like take one proton away and add the rest. I don't know why I put 3 there. That should be 2.
And then if it's the secondary, then you have to bring the R and be RNH.
For secondary, it would just be R2N.
Okay, yeah.
You get rid of 1 H every time. Okay, so we have this reaction. So this reaction, what do you think is like the missing reagent, the missing nucleophile here? Okay, yeah. So he's been like waiting for this moment. So all we do in the reaction, we saw that OH was replaced with the amine. So all we do, we take this amine, we add an H to it, and that's how you get your nucleophile. So you know, this was actually what? So H2N with the ethyl. So this is where we have to consider reactivity. So if you remember the order of reactivity, the carboxylic acid is just slightly more reactive than the amide. So the amide is the worst, but the carboxylic acid is the second worst. So doing this reaction, if we just give it an amine, like this would happen, but it wouldn't happen in good yield because the carboxylic acid is not much more reactive than the amide. Like the reason that it's so successful with the acid chloride, like that's why making an amide from an acid chloride is so successful, is because the chlorine is so ready to leave. Like it's very easy to change the acid chloride into whatever you want. But down here, it's very hard to change the carboxylic acid to an amide when the carboxylic acid is so unreactive. So this is why when you're doing stuff with carboxylic acids, you usually go through the acid chloride intermediate. So we usually use like something like Sokol to turn it into a chloride and then do whatever you want. So like for this, a more realistic way would be converting it to an acid chloride first. So now you have the super reactive acid chloride. You can do whatever reaction you want. You can turn it into any carboxyl derivative that you want. So yeah, so now if we take the same nucleophile, if we take that same amine, and we do the attack happens much faster, having a much better yield. So this is just like a better synthesis.
So the top one with the carboxylic acid can occur. It's just
Yeah, it will, but it's so much better to go through the acid chloride. Okay. Okay, so I'll do this acid anhydride synthesis later, but there was like a point I wanted to make. So for the acid anhydride, similar to the acid chloride, it can go to a bunch of different molecules. So let's say we gave an acid anhydride water. What happens? Carboxylic acid. So the water is going to go in, attack the carbonyl, and remember, in an acid anhydride, this whole thing is the leaving group. So this whole thing is going to pop off. And then what about ROH? What about alcohol? We get an ester, yeah. So then we get an OR. If we do like an amine primary, either NH3 primary or secondary, we get an amide. And then the last one is stupid, no one cares about it, but Wes had it, so I put it. It's reduction again. So when you reduce it, it turns into an aldehyde. Okay, so here's the point I wanted to make. So if we look at the little chart for like the acid chlorides, we could go to all the carboxyl derivatives. We could go to every single one. I didn't include the sulfur one because nobody cares about it. So all the like relevant derivatives I added. So you can see the carboxylic or the acyl chloride can go to the acid anhydride because the acyl chloride is more reactive than the acid anhydride. But when we go down to the acid anhydride chart, there's no arrow going towards acyl chloride. So you can't really go like upstream the order of reactivity. You can't like go to a carboxyl derivative that's more reactive. So if we look at like our list, it's very easy to go downstream. It's very easy to go from like an acid chloride to like an ester, but you can't go from like an ester to an acid anhydride because of the reactivity of the leaving groups. So you always have to keep that in mind. Yep. So when you're doing these chapter 17 reactions, they're very straightforward. They're very simple. All you have to do, you take the nucleophile, you replace the leaving group. But you have to consider like the leaving group's reactivity. So in this order of reactivity, it's super easy to go like downstream it. So it's very easy to go from an acid chloride to like a carboxylic acid. But you can't like go backwards. You can't go upstream the reactivity. So you can't go from like a carboxylic acid to an acid anhydride. Because like if we attacked with this as a nucleophile, if we attacked a carboxylic acid with that nucleophile, it's not reactive enough to like do the reaction. But if we attack this with H2O, it is reactive enough to turn into a carboxylic acid. That's the only thought you have to put into this chapter. And the rest is literally just like blind, like copying and pasting with the nucleophile. So if that makes sense. And if you want, it's up to you. We can stop here or we could finish like those two reactions of acid anhydrides. Okay. So to make acid anhydrides, there's a couple ways. So with this one, if you mix a carboxylic acid and an acyl chloride, you get the acid anhydride. So this happens because the alcohol is going to go and attack the chloride because the chloride is so reactive. It's going to go in and attack there and make your acid anhydride. Okay, so the next one, what's the next one? Oh yeah, so if you just keep this up, so let's say you have like a carboxylic acid or like a dicarboxylic acid, and you have like a sufficient amount of carbons. So in this one, it's like a 3, 4. It's like a 4 carbon chain. So what happens here when you give this heat, it's gonna like join together to make an acid anhydride. So like one alcohol goes in and just like kicks out the other one. So in the end, we end up with like a 5-membered ring. And it only works if you have like this number of carbons in between. So like it only works if you can make like a 5-membered ring or like a 6-membered ring. It's possible probably to get like a 2 or like a 3 or 4-membered ring. It would probably just be like really low yield.
It picks up all the other.
Yeah.
You already need to see.
Yeah. Okay, so that's it. I will see you tomorrow. Yeah. What's, oh,
Files.